answering questions in lab, okay? We're looking at chapter 37. We're talking about chapter 6, question 37. The book doesn't even have 37 chapters. So that's an achievement right there. I've actually written chapters that don't exist. So the question is, ethyl acetate, of course, reacts with hydrogen gas in the presence of a catalyst to yield ethanol. Here, of course, therefore, is this molecule right here is ethanol, just so you guys know. And this right here is the molecular formula for the ethyl acetate. Not something you need to be able to recognize or name in this course, but if you were to take 306, then it would be something you would be potentially capable of doing, because 306 is essentially organic chemistry, an intro to. So write the balanced equation for the reaction. Pretty straightforward, I believe. Does anyone want me to go through and balance the equation? Are you guys good with moving on from that? You go through it? No problem. Okay, here's what I do. I go carbon, hydrogen, and oxygen as a way to keep track of things. How many carbons on one side? I've got 4, and I've got 2, and then hydrogens, I've got 8 plus 2 is 10. And then on the other side, I've got 6. And then finally, I've got 2 oxygens plus, so just 2 oxygens on one side and 1 on the other. Good so far? Any concerns about those numbers? Did I miss anything? Did I count wrong anywhere? Okay, good, 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 good. Okay, if we're all on the same page, then moving forward, what we do is then, of course, C4H8O2 plus H2, and this is a liquid, this is a gas, becoming C2H6O, a liquid. First question I have for you guys is, what type of reaction is this? Got 2 things on the reactant side. So you've got 2 reactants, and you end up with 1 product. So this is actually a, there's only 1 name for this reaction. Well, okay, there's 1 primary name for this reaction. It's a combination reaction or a synthesis reaction, okay? This is a synthesis. And then in essence, you could call this reaction the synthesis of ethanol from ethyl acetate. Okay, you're synthesizing ethanol from ethyl acetate. Good so far? Okay, if you guys are comfortable with that, then let's very quickly balance this equation. So I would have started with a 2 here. All right, that's the first instinct to do in general. I go, okay, because I've got 4 carbons on one side, 2 on the other. Putting a 2 there gives me 4 carbons and 12 hydrogens. So I go 4 and 12. And finally, I end up with 2 oxygens. Good so far. Okay. Now, my carbons are balanced and my oxygens are balanced. The only thing that is not balanced are my hydrogens. That makes sense? Okay. So I've currently got 10 hydrogens on one side and 12 on the other. And so if I come along and put a 2 here, that's 2 times 2 is 4. 4 plus 8 is now 12. Okay, any questions about that? You guys comfortable with how I balance that? Does that make sense? Okay, and that's why I like to do a little mechanism like this right here too, to help myself track the quantities of each element. Okay. Good so far. Okay, if that makes sense, if you guys are comfortable with that one, then I'll move forward to part B. Part B. How many moles of ethanol are produced by reaction of 1.5 moles of ethyl acetate? Okay, don't forget our balanced equation, of course. We've got a 2 right here and a 2 right here. That's going to come back to haunt me because I put the unbalanced equation on every page for this now. That's okay. It's pretty easy to balance. Good so far? Okay, so the question is, how many moles of ethanol are produced by reaction of 1.5 moles of ethyl acetate? So we go 1.5 moles of ethyl acetate. And you could write the formula instead, probably actually easier to do. Actually easier to write the formula formulas typically do tend to be easier to write. So you can write C4H8O2 over 1. Now, what is the ratio of ethyl acetate to ethanol? It is a 1 to 2. 1, well, 2 on top. You can call it a 2 to 1 or 1 to 2, just regarding, depending on where you put things. So it is 1 on the bottom, ethyl acetate, C4H8O2, to 2 moles and moles of C2H6O. Okay, good so far? Okay. Like so. Okay, when you do that, now you can see that the moles of ethyl acetate will cancel with moles of ethyl acetate as far as units go, because these are our units, moles of ethyl acetate. Then it's 1.5 times 2, giving us 3 moles of C2H6O. Good so far? Any questions? All right, so that's part B. Moving on to part C. Maintaining our balanced equation, in case we need it again. How many grams of ethanol are produced by reaction of 1.5 moles of ethyl acetate with hydrogen gas? So we can actually do that entire calculation again. We know the answer to part of this, technically, but I'm going to write out the whole thing so you can see how these things work out, okay? So we start again with 1.5 moles of our ethyl acetate, C4H8O2 over 1. And then we have a 2 moles of C2H6O to 1 mole of C4H8O2. And finally, what we need here is the molar mass of ethanol, C2H6O, which is go 2 times 12.01 grams per mole for carbon. And then we have our hydrogen, which is 6 times 1.008 grams per mole of hydrogen. And finally, 1 oxygen atom times 16.00 grams per mole of oxygen. Now, this is going to be approximately 2 times 12.01, which is about 24, plus something close to 6. So 24 plus 6 is about 30. 30 plus 16 is therefore 46. It's a little bit over 46. You can even go with how much it actually is. 6 times 008 here would give us 0.048 for our decimal there, and the 0.2 there is 0.02 there. So we'd actually end up with 0.05 total. So it's 46.05 grams per mole C2H6O. All right, good so far? Okay. Finally, therefore, you can see we need to put here, we need to do 46.05 grams of C2H6O5 per 1 mole of C2H6O. Plug that into your calculators from there, and you'll get the final answer. Now, what is that final answer? It's actually going to be 3. It's going to be 2 times 3. So it's 3 times this value, which gives us 5.1. 3 times 6 is 18. So 8 carry the 1. 3 times 4 is 12. Plus 1 is 138.15 grams. Okay. Question? Use what's available to you on the periodic table. Yeah, use what's available to you on the periodic table. That's the best option. Generally, you won't lose points if you round things off, but I encourage you not to round things off because it's not a good habit to get into, is just constantly rounding things or approximating things. It's good if you are in a real hurry, but we don't want them rounding off pennies when it comes to what money we have to pay for bills, like that. So let's not round if we can help it. Good so far? Okay, that's question C. Did I go too fast for anyone? You guys following me? Okay. Question D, how many grams of ethanol are produced by reaction with 12 grams of ethyl acetate? So then we would have to start with the 12 grams of C4H8O2. 1. And we know then, now what is the molar mass of ethyl acetate? 4 times 12.01 plus 8 times 1.008 there, plus 2 times 16. This is a point at which I go, okay, yeah, I kind of wish I did have my calculator, just because I'm feeling a little tired and a little lazy, and calculations can cause the brain to start to go, hey, I'd like some water. So 4 times 12.01 plus 6 times 1.008 plus 32 gives you 86.008. So, okay. So it's then 1 mole of C4H8. Oh, and I made a mistake too. This should be an 8, and I think I put a 6 into my calculator. So that value is actually wrong. Let's see here. So 12.01 times 4 plus 8 times 1.008 plus 32 is actually 88.104. Easy to make a mistake if you're not paying close attention. There it is. So 1 mole of C4H8O2 over 88.104 grams of C4H8O2, like so. Then we utilize our ratio, that is the 2 moles of ethanol to 1 mole of C4H8O2. And finally, the molar mass, which we have back here, is 46.05. 46.05 grams of C2H6O to 1 mole of C2H6O. So plug that into your calculators now. So it's 12 divided by 88.104 multiplied by 2, and then multiplied by 46.05. And I get 12.544, so on and so forth, grams of C2H6O. How we doing? Any questions? That help so far? Make sense so far? Question? Because it asks how many grams of ethanol, right there. So if you follow your units carefully, which is always this is one of the reasons why I'm labeling everything with units, is so that I can follow my units. So I started with grams of ethyl acetate here. 1 mole of ethyl acetate to 88.104 grams of ethyl acetate. You can see grams of ethyl acetate cancel, right? We're left with moles of ethyl acetate. Okay, so we've got moles of ethyl acetate. Now this guy right here, the mole ratio from the balanced equation, moles of ethanol on top, 1 mole of ethyl acetate on the bottom. You see moles of ethyl acetate cancel, and that will leave us with moles of ethanol. And the question wants us to answer with how many grams of ethanol. So right now, if I stopped here, if I didn't add this guy here, if I just stopped here, I would have moles of ethanol. This is needed because here, now I've got grams of ethanol per moles of ethanol. And moles of ethanol will cancel with moles of ethanol, leaving me with units of grams of ethanol. That makes sense? Fantastic. Good. That is what we're going for. Okay, other questions? That's why it's really important to label your units too, because then you can see the question asked you for grams of ethanol, and you will end up answering correctly in grams of ethanol because your units will cancel properly. Like so. Now, my question to you guys is, on this question, how many significant figures should I actually answer with? If I were basing this off of significant figures, how many significant figures should this final answer have? 2. If we were looking at significant figures, the only value we were given that has a defined number of significant figures is right there. That determines our significant figures right there. So that's 2 significant figures there. And on this one, here you can see we've got, that would be 3 significant figures. Okay. Good so far? Okay, good. So we've got 2 significant figures for the answer to C, 3 significant figures to the answer for D. And finally, E, how many grams of hydrogen gas are needed to react with 12.0 grams of ethyl acetate? This one, again, our balanced equation. You guys comfortable? Do you guys want me to go through this one, or would you like to just skip it? Are you good with how to do this? Does it make sense to you how to do this? You guys follow how to do it? Okay. What can help is, if you are at all still lost, writing yourself out a map of how you need to do what you need to do is a good place to go. So go with, where do I start? You can see that is the information you have. You can go mass of C4H8O2 is what I start with. Now there's going to be some steps in here. And what am I trying to answer? My answer, my endpoint, my goal, my destination is mass of H2, right? So in order to get mass of H2, I know I need moles of H2. That's going to be a step, okay? Moles of H2 is going to have to come from, therefore, moles of C4H8O2. And you know then that what you need are the molar mass of C4H8O2 here. Here you need the mole ratio of C4H8O2 to H2. And finally, here you'll need probably the easiest molar mass to calculate in this entire question, the molar mass of H2. Does that make sense? Okay. So I'll just show you guys the general idea of how to do that answer instead of writing it out and going through the entire thing. Good? Okay. Awesome. No problem. All right. Any questions about this problem on the homework? Question number 37 from chapter 6. That helpful? Okay. Then let's move to the next question. Question 43 from chapter 6. So titanium metal is obtained from the mineral rutile, which is primarily composed of titanium 4 oxide. The process requires multiple steps as shown in the following reactions. So you can see that this is 1 reaction and this is 2 reactions. You know that you've been given a balanced reaction, most likely because you have coefficients present. Usually it's very silly to give someone coefficients unless you've actually correctly balanced the equation. So write mole ratios to show the relationships between the reactants and products for each reaction. So with that in mind, that means you will need to write 6 ratios for equation 1, and you will need to write 4 ratios for equation 2. That makes sense, guys? You need to relate all of the, let's see, relationship between the reactants and products for, okay, so this is, and this, these are for connecting product to reactant. It doesn't specify just connecting the products to the reactant. Okay. Actually, I guess it does. Between the reactants and products for each reaction. Technically, there are more. There are actually, for equation 1, you could do ratios of the reactants to the reactants, and you could do it also ratios of the products to the products. Okay. And those are the ones I'm actually going to do. The reason I'm going to do that is I want you guys to still be able to take what I've explained and answer this question as well. Okay. So the question, let's see, does it actually do that? How many moles of that? Okay. Yeah. Okay. So the question I'm going to ask is, what are the ratios of reactant to reactant and product to product? That makes sense? The questions so the original one was asking, what is the ratio of reactant to product for the entire thing? So what is the ratio of titanium 4 oxide to titanium 4 chloride? What is the ratio of diatomic chlorine to titanium 4 chloride? What is the ratio of carbon to titanium 4 chloride? What is the ratio of this one to that, this one to that, and this one to that? Okay. And then you go down here. What is the ratio of this to this one, this to that one, this to this one, and this to that one? Does that make sense? Any questions about that? Let me put it this way. If I label these A, B, C, D, and E, for example, find the ratio of A to D, A to E, B to D, B to E, and C to D, and C to E. Does that make sense? Okay. Find those ratios and then do the similar thing for reaction number 2. That's what question A is asking. Okay. Instead, for you guys, I'm going to show you what are the ratios of reactant to reactant and product to product. For example, the ratio of titanium 4 oxide to chlorine gas, diatomic chlorine, is what? It is 1 to 2. Okay, coming from your coefficients. You just keep your coefficients there. The ratio of titanium 4 oxide to carbon is 1 to 2. And the relationship between carbon and diatomic chlorine, it's either 2 to 2, or you can make your lives easier and go, well, that actually reduces to 1 to 1. Making your lives easy. 2 divided by 2 is simply 1 to 1. Then you can come through and do the same thing for the carbon dioxide and the titanium 4 chloride. So titanium 4 chloride to carbon monoxide is a 1 to 2. Okay? Make sense? Any questions? You guys want me to do equation 2, or are you good with just that? Does that help at all? Does that clarify? Where are we at? Good? Anyone want to see more relationships, ratios? That's fine if you do, but please let me know. Good? Okay. Then I'm going to move forward to part B. How many moles of titanium for oxide are needed to form 1 mole of titanium? Titanium 4 oxide is right here. And here is titanium. So how many moles of titanium 4 oxide are needed to form 1 mole of titanium? Okay. In order to do that, do you guys see the map that you need to create? You have to utilize these 2 reactions. So there's 2 reactions here, 1 and 2, and we need something that connects them. What connects these 2 reactions? The titanium 4 chloride right here. This will actually go away. There we go. Titanium 4 chloride right there is present in reactions 1 and 2. Okay. So we need to start with, we're actually going to work backwards here. Okay. Essentially, we're going to say we want 1 mole of titanium how many moles of titanium 4 oxide, therefore, do we need? We're going to start with our 1 mole of titanium. We're going to get from that moles of titanium 4 chloride. And then from moles of titanium 4 chloride, we're going to connect that to titanium 4 oxide. That makes sense? So what we're going to do then is utilize here the ratio of titanium to titanium 4 chloride, and here the ratio of titanium 4 chloride to titanium 4 oxide. Make sense? So what you do is you go 1 mole of, there should be 2 there, 1 mole of titanium to, what's our ratio? It is to 1 mole of titanium, we have 1 mole of titanium 4 chloride. This comes from equation 2. And now, utilizing equation 1, we'll start with 1 mole of titanium 4 chloride on the bottom because we want our units to cancel. So we know we're going to start with titanium 4 chloride on the bottom because we need our units to cancel. And the relationship between titanium 4 chloride and titanium 4 oxide is also 1 to 1. 1 mole of titanium 4 oxide, like so. And so it actually turns out that all we need is 1 mole of titanium 4 oxide. Because it's 1 to 1 to 1. Technically, yes. Yes and no. The problem is, the reason this question exists is to get you guys to see the importance of the coefficients and how they work even across multiple reactions. And this setup actually becomes important because what you're doing is you are now looking at, what you're actually looking at is you're actually utilizing the conversion factors. And so the units will only cancel if you lay this out in this fashion. Technically. Yeah. It feels like a lot of effort to arrive at the answer of 1. I agree. But that's actually part of the beauty of this question in some ways, is because it's not a complex set of calculations. You don't need your calculator for this. It gets you to look at the ratios and to look at unit cancellations without actually having to do a lot of complicated math. This should be math that you can do in your head, even when you're tired. You should be able to do this math in your head, right? Even if you are someone that struggles with math, this should be math that you can do. This should be. Okay. Good so far? Okay. I do understand where you're coming from. You're a little bit, you're going, why do I bother when it's 1 is equal to 1? Well, because it's not about complicated arithmetic. It's about the unit cancellations and the concepts of the multiple ratio. So finally, how many kilograms of rutile are needed to produce 95 kilograms of titanium? Now this is, again, easier than it looks because we've already established the cancellation of 1 to 1 to 1, right? Rutile, as the question indicates, rutile is titanium 4 oxide. Okay. So the only things we need here then are molar masses. Now. We need the molar masses of titanium. Let's see, titanium is, what is titanium? 47? 47.88. So titanium is 47.88 grams of titanium per mole of titanium. And then titanium 4 oxide will be 47.88 plus 32, which brings us to a grand total of, let's see, I can do this on my head, 79.88, if I believe. Should still be able to do that. Grams of titanium 4 oxide per mole of titanium 4 oxide. So what does that leave us at? Well, a lot more writing than is necessary, of course. Here's where we start. We go 95 kilograms of titanium. And yes, if this were an exam question, the setup takes longer than it does for you to do the calculation. I agree. Okay. 1,000 grams of titanium to 1 kilogram of titanium. And then, of course, here's where you bring in the molar mass to begin with. 47 grams of titanium to 1 mole of titanium. Then we go 1 mole of titanium 4 chloride to 1 mole of titanium, and 1 mole of rutile titanium 4 oxide to 1 mole of titanium 4 chloride, and finally 79.88 grams of rutile to 1 mole of rutile. And really what you end up doing is 95,000 divided by 47. So 95,000 divided by 47 multiplied by 79.88. Oh yes, and of course I forgot one more conversion factor. You need to multiply in there again then 1 kilogram of titanium of rutile to 1,000 grams of rutile. So technically you could have just started with 95, because you see the 1,000 and 1,000 cancel each other out as well very nicely. So really it's 95 divided by 47 multiplied by 79.88 at the end of the day, giving us 161.46 kilograms of rutile before we look at significant figures. And technically, this is something where I would probably just say, give me, I probably wouldn't ask for significant figures here, because this is a value that has an implied decimal, and I really don't like implied decimal. So this honestly would be a question where I would not ask for significant figures unless I gave you a value with a decimal. Okay. And at the end of the day, we end up with something on the order of about 161 kilograms of rutile is what we started with in order to yield 95 kilograms of titanium. Questions? Any question? You guys good? Okay, so we got that one done. Finally, the remaining question is not how. What are percent yield and theoretical yield and actual yield? So in order to be able to answer this question fully, we have to say actual yield is the yield measured experimentally in the lab setting, or just measured when you do an experiment. You do an experiment, you take a measurement, that is your actual yield. It is the actual real yield of what you have in your hand at the end of the day. Okay? Your actual yield is what you've actually yielded in the lab. That makes sense? Okay. The actual yield is what you actually arrive at the end of the day. Your theoretical yield is going to be what you calculate from stoichiometry. So all these calculations that we're doing with stoichiometry, when you're utilizing the molar mass and you're utilizing mole to mole ratios and you're converting from grams to moles to moles, and then moles to grams again, those are theoretical calculations. You're not actually doing the experiment. You're starting with a quantity and you're doing a theoretical calculation. Does that make sense? Stoichiometry are theoretical calculations. Okay. So there's your actual yield and your theoretical yield. Now, are there any questions about that so far? Pardon? Clear so far? Okay. Then the final thing is, what is percent yield? Now, percent yield is simply actual yield divided by theoretical multiplied by 100 to give you a percent. And that's it. That's all it is. And if keep in mind, your actual yield must always be smaller than your theoretical yield. The reason for that is actual yield is always going to be smaller than theoretical yield if you actually made no mistakes. Okay. If you have not made any mistakes, then the actual yield that you could obtain could never be larger than 100%. You cannot create matter that does not exist. We live in a world that obeys the laws of physics, that obeys the lack of miracles and the existence of magic. Magic does not exist in this universe, so therefore we cannot conduct alchemy. We cannot convert things into things they are not. Therefore, you can only yield the amount of matter that already exists there at most. Okay? Your actual yield will be equal to or less than your theoretical yield. You will always end up with at most 100%. And anything else that is greater than 100% clearly indicates things that have gone wrong in the lab. That makes sense, guys? Okay, fantastic. Then we will stop sharing here and we will end this